Okay, so it's time to introduce our final speaker for the afternoon. Let me just remind everyone that if you have questions, you can raise your hand during the talk and we will call on you, or there will be a question and answer session at the end. Another thing you can do is send a message to everyone in chat, and there can be a discussion about it going on behind the scenes. So it's a great pleasure to introduce Lara Anderson of Virginia Tech. We'll talk about twisted dimensional reductions in F-theory.
Thank you very much. I'd like to thank the organizers for inviting me to be a part of this conference and for putting together a really interesting roster of talks for the week. I'm looking forward to hearing much more as the week goes on. And thank you all also for hanging in there into late at night in various time zones to participate. I got a message when I was invited to speak from the organizers saying that because of the very diverse math and physics audience for this, to try and make our talks as a sort of general audience as possible. For the stuff that I want to talk about today, as for many others, there's a lot of moving parts, and that's sometimes a tricky thing to do. But my goal for today is to do less about the details of the F-theory compactifications that I am studying here, and more about the sort of general arena of these questions and some of the broader open topics and motivation behind this. So hopefully this will work. The work that I'm going to focus on for the most part today is done in collaboration with my colleague James Gray at VT and Paul Ullman, who is now a postdoc in Uppsala. This is a paper that should appear very soon. I'm also going to sort of put this in context of older work that was done by myself and James, as well as our postdocs at the time, Xin Gao and Sungju Lee, now faculty at Sichuan University and the Institute for Basic Science in Korea, and our talented undergraduate, Brian Hammock. So with that in hand, let me start by a bit of motivation for the stuff that I'm going to tell you about today. A long-term goal across different aspects of string theory is to try and get as comprehensive as possible an understanding of possible string effective theories in various dimensions. The very robust string swampland program that has attracted lots of interest in recent years is one example of an arena in which you can ask these questions. Within the subject of string compactifications, of course, the question of what effective field theories is intrinsically linked to the questions of which geometries you can dimensionally reduce string theories on. So even for the simplest class of Calabi-Yau compactifications, which are going on 30 years of being studied, compactification manifolds, Calabi-Yau compactifications for 30 years, we have yet to understand all that much about the general set of such manifolds for Calabi-Yau n-folds when n is greater than 2. For example, we do not know if there's a finite number of such topological manifolds. Even weaker questions, such as can you bound the topology of Calabi-Yau threefolds, their Chern classes and intersection numbers, all of these are things that string theorists would very much like to understand. So I do not know the answers to any of those questions, but I'm going to outline some aspects, or at least an approach to trying to address some of these questions via talking about Calabi-Yau fibrations. And this is the broad arena that I want to sort of introduce with this talk. So quick reminder, which I'm sure is known to everybody, definition of a fibration: we have a surjective morphism between two spaces, X and B, such that for all points in the base, or at least almost all points, the inverse image of that projection is homotopic. And if we have a continuous mapping from the base, i.e. the target of that projection, back up to the total fibration, then we say that we have a section to that fibration. So fibrations play an extremely key role in string dualities. For example, F-theory, M-theory duality via elliptic fibrations, heterotic F-theory duality via elliptic and K3 fibrations, heterotic type 2A, etc. In addition, this question of sort of what geometries are possible takes a simpler form in the case that you have a fibrid manifold, and that you can classify possible fibers and bases independently and then sort of put them together like Legos. This increases the calculability. You can say a lot about the form of cohomology groups of intersection numbers, possibly even the metric in such a setting. Now, how does the existence of a fibration give you a possible window into finiteness? Well, for starters, these are the only sets of Calabi-Yau manifolds for which we know anything about the finiteness. And in particular, we know that the set of all genus 1 fibred manifolds, Calabi-Yau threefolds, was shown to be finite by the work of Gross and Grassi back in '93. And much more recently, Dicierbo and Svaldi have shown that there's a finite number of bases for elliptically fibred 4 and 5 folds. They're working towards essentially the same structure of proof that Gross did in '93 for these higher dimensional Calabi-Yaus. Just a word on terminology. Here I'm referring to an elliptically fibered manifold or a genus 1 fibered manifold. What is the difference between those two and why do we care? If a section exists to the fibration, then we upgrade the topological definition of the fiber as a torus or a genus 1 curve into an elliptic curve by giving it a marked point on each fiber. So elliptic refers to geometries with a section to the fibration. So schematically, what is the picture? We have a base manifold with a projection, fibers above it. And in the case that you have a section, this, in a case of a holomorphic section, would pick out a single point on every fiber. Rational sections can do the same thing on almost every fiber, wrapping some reducible components of fibers at higher codimension. And if you have a multi-section, that will intersect each fiber generically as an n-sheeted cover of the base. So you can have n intersections. So again, genus 1, this will be multi-sections, elliptic, single intersection with the fiber. Okay, again, broad question, why do we care? Why are we talking about this? A few things are known about Calabi-Yau Again, I'm going to be focusing on n greater than 2 here for this talk. Calabi-Yau folds can only be fibered by Calabi-Yau folds, i.e. manifolds with C1 equals 0, and this can happen for m less than n. In addition, for n greater than 2, the existence of a fibration is a deformation invariant statement for a Calabi-Yau manifold, in particular for a Calabi-Yau threefold. So everything in the topological family will exhibit a fibration if one exists at all. The motivation, again, behind Gross's theorem of classifying these genus 1 fibered manifolds was indeed to try and ask, can you say something more broadly by understanding where elliptic Calabi-Yaus or genus 1 fibered Calabi-Yaus fit within the set of all manifolds? Perhaps if you understand that substructure, then you can understand something about how all Calabi-Yau threefolds, for example, extend away. And the hope might be, we certainly know there are lots of Calabi-Yau threefolds that are not fibered, for example, the quintic hypersurface in CP4, but for almost all the examples we'll know of, and I'll talk more about this, it is the case that simple geometric transitions, such as conifold or flop transitions, can produce a fibered manifold. So the hope is by studying genus 1 fibered geometries and where they live in the space of all Calabi-Yaus, perhaps you can understand something about how to enumerate Calabi-Yaus more generally. Specifically, understand this and then understand the geometric transitions that break that structure in order to try and characterize Calabi-Yaus. Now, this is, of course, a broad set of questions. So let me try and give a little bit of insight into, again, why this is quasi-tractable and then what type of physics we hope to extract. So you might say, okay, great, we know that there's a finite subset of Calabi-Yaus, but perhaps it's an extremely small subset and we can't necessarily say anything very general about Calabi-Yau threefolds by studying elliptic or genus 1. However, you might say that, but a couple of observations. First, it's possible to construct very large data sets of Calabi-Yau elliptic fibrations. And again, this is using this sort of modular build a base, build an elliptic fiber over it. Specifically, people like Morrison and Taylor built a very large set of Calabi-Yau threefolds by using toric surfaces as bases and tacking on an elliptic fiber with a single section over the top of it. Wadi and I did similar work for Calabi-Yau fourfolds. This has been done by Huang and Taylor, Halvorsen, Spedic, many other people have tried to sort of modularly build Calabi-Yau fourfolds and threefolds in very vast data sets. And you can see from that approach that you can saturate most known Hodge numbers very rapidly with that approach. Again, not hugely compelling in its own right, but an interesting observation. Moreover, perhaps a stronger statement, one can ask about how, if you pick a generic Calabi-Yau manifold, a Calabi-Yau threefold within the data sets that we understand so far, how many of those known constructed Calabi-Yau threefolds admit Calabi-Yau fibrations, i.e. genus 1 fibrations? So this question has been asked in recent years by my collaborators and myself, as well as by Wadi Taylor's group at MIT in great detail. You can consider your favorite data set, for example, the data set of toric hypersurfaces, 500 million toric polytopes put together by Kreutzer and Skarka, complete intersection Calabi-Yau manifolds, the oldest data set of manifolds built in simple projective spaces as complete intersections, any of these data sets. And you can say, can I hunt for the existence of genus 1 fibrations and understand how ubiquitous they are? The immediate observation that you make as soon as you start playing with this is that almost all known 3 and 4 folds actually are fibered. And in general, generic manifolds do not admit just one elliptic or genus 1 fibration. They admit many, order tens, hundreds, or thousands, or in one case, actually an infinite number, as I'll talk more about in a second. So how does that work? So if you take the known, this is the Kreutzer-Skarka set of Hodge numbers that arise out of that 500 million toric polytopes, and you look at this data set and say how many of those Hodge numbers are saturated by known elliptic manifolds. Back in 2012, Wadi printed this out. This is a much denser set of dots now, thanks to recent work. But this was first studied for toric data sets, hunting for fibrations by various people about a decade ago. For Calabi-Yau CC3-folds, this is the set of 7,890 manifolds written down by Candelas and collaborators. You can hunt for an obvious fibration. So this notation is probably not familiar to everyone and isn't super important for what I want to say, but let me just briefly outline it. This matrix notation is indicating an ambient space, in this case, a product of simple complex projective spaces, P2, P1, P2. And these entries in the matrix, each column is giving the multi-degree of two defining equations, in this case, in this ambient space. So this is a complete intersection variety, two defining equations of given degree, producing a Calabi-Yau threefold. So the first equation here is a 1,3 hypersurface in P1 times P2. This is a rational elliptic surface. If I solve that first equation and plug it into the second one, that will leave me with a cubic in P2, hence an elliptic fiber over every point of the rational elliptic surface. This is the famous Schön threefold with Hodge numbers 1919. So the point I'm making here is that if you just inspect given data sets, you can immediately see from the structure of the defining equations that this thing will be genus 1 fibrid. Likewise, you can do this for Calabi-Yau fourfolds and products of projective spaces. That was done by Gray, Haupt, and Lucas. And you can immediately see just from this very obvious search for fibration structure in the defining setup of the equations that about 99% of those data sets admit fibrations. And one other point I was going to make on that, in general, the thing you can say as well is not just elliptic or genus 1 fibrations, but whatever dimensionality of manifold you're building, sort of all possible Calabi-Yau subfibers are possible. So here in blue, red, and green, this is the definition of a complete intersection Calabi-Yau fourfold. The blue highlighted multi-degrees here are the definition of an elliptic fiber for this manifold. The red and the blue are a K3 fiber, and the green, red, and blue define a Calabi-Yau threefold fibration over P1 inside this fourfold. Okay. In addition, as I mentioned previously, when these manifolds have fibrations, they generically do not admit just one. In fact, there can be many different fibrations, topologically distinct fibrations in the same Calabi-Yau threefold. So as an example, if I start with one complete intersection manifold, I can rearrange rows and columns, which don't change the definition of what manifold I'm interested in, to write this as an elliptic fiber over a 1-1-1 hypersurface in a product of 3 P1s, or over P1 times P1. The number of fibrations per configuration can be enumerated for both threefolds and fourfolds. The caveat to all of this, of course, is that these are just obvious fibrations, i.e. these are fibrations you can spot by looking at the defining equations. And with my colleagues about 5 years ago, we attempted to do better and actually write down topological criteria for a fibration to exist independent of whether that's sort of manifestly realized from the algebraic description of the manifold. And we started with a very simple data set of Calabi-Yau threefolds to try and enumerate all fibrations, specifically the CC threefold data set of 7,890 manifolds. And there we found about 100,000 genus 1 fibrations, 30,000 K3 fibrations, and 208 nested fibrations. They were obviously fibred. Once you upgraded that to non-obviously fibred, we found that greater than 99.4% of all those manifolds were fibred. And specifically, we classified about 300,000 fibrations. And in various manifolds, we could find a truly vast number of fibrations. So for example, there's one of these manifolds that was an anti-canonical hypersurface in a product of 2D-P7s that gave rise to 15,000 inequivalent genus 1 fibrations. And for one manifold, the famous Schön manifold, there's in fact an infinite set of distinct elliptic fibrations. This was studied by Aguiso, Aspinwall, and Gross as well. Okay, so what is the point? Again, takeaway message. If you throw a dart at the data set of Calabi-Yaus that we know about, generically everything admits fibrations. So if you understand fibration structure, if you understand what is possible to build, if you can enumerate and classify fibrations, you have a very good chance of at least understanding the Calabi-Yaus that we know about already. Now you might say maybe this is a byproduct of complete intersection structure in toric varieties. Maybe there's more general constructions of Calabi-Yaus that won't share these features, and that's certainly true. But for the manifolds that we know about already, either they are all fibered or we have strong evidence that they are connected very simply by geometric transitions to ones that are. I should say that I don't have time to talk about this today, but these results were basically all for manifolds that were simply connected. And with my collaborators, we also extended this to non-simply connected Calabi-Yau threefolds and found the same structure persisted. Okay, that was all a bit of motivation to try and set the stage for the work I want to talk to you about today. So the question today is actually, I have hopefully made the point so far that genus 1 fibered Calabi-Yau threefolds and fourfolds are extremely ubiquitous within known compactification geometries. So I also mentioned that lots of prior work had enumerated possible elliptic fibrations very systematically, for example, the work of Morrison and Taylor. However, although the genericity statements for Calabi-Yaus are about genus 1 fibrations, the actual systematic constructions have been more for elliptic fibrations. So I want to illustrate a couple important questions that still remain unexplored regarding genus 1 fibrations and how to characterize their geometric properties as well as the associated physics. Again, the goal of this is to try and understand something about broadly the data set of Calabi-Yau threefolds and the field theories that can arise from them in string compactifications. So with that in hand, I need a little bit more substructure for these fibered manifolds to be able to describe the points of interest. Within the discussion of elliptically fibered manifolds, there's an extremely powerful theorem due to Nakayama, which is that any elliptically fibered threefold is in fact birational to a very simple type of elliptic fibration known as a Weierstrass model. Weierstrass models were introduced by Deligne for elliptic curves and Nakayama for elliptic fibrations. Schematically, they're defining an elliptic fibration via a cubic constraint within a manifold defined as the projectivization of 3 line bundles, like so. The Calabi-Yau condition in this context fixes the line bundles that you're projectivizing. Sorry, this last O should be an L there. This Calabi-Yau condition tells you the degree of the line bundle that you're projectivizing. And in given a mystery manifold that is an elliptic fibration, if you have a section, you can use it to explicitly build coordinates of the form X, Y, and Z of these weights and explicitly write down a Weierstrass model. Geometrically, the idea behind Weierstrass models is that you're blowing down components of reducible elliptic fibers. Anything that doesn't intersect your zero section gets blown down, and this leaves you with a minimal form of the elliptic fibration with a single section. The physicist version of this structure is a variable change to describe that fiber as a degree 6 hypersurface in P123. Okay, now for a bit of field theory to go with this geometry. Weierstrass models come about very naturally from the early days of string constructions into F theory, because F theory is the geometrization of the type 2B string theory, with mutually non-local 7 branes. So the idea is that an elliptic threefold X over B can encode information about type 2B compactified over this base manifold B in the following way. Type 2B comes with an axiodilaton with SL2Z symmetry. This happens to be the symmetry of a 2 torus. So if you can encode information about the tau function of that 2 torus point by point, you can use that as a geometrization of information about the axiodilaton in a type 2B theory. These two T2 degenerations, in fact, for a fibration, that T2 can degenerate over higher codimension in the base. And this corresponds very significantly in the type 2B theory to 7 branes classified at codimension 1 in the base by Kodaira and Tate. The reason this construction is interesting is that this is encoding information about field theory and geometry. You build me an elliptically fibered threefold, and we can read off information about strongly coupled type 2B. Weierstrass models are natural in this case because you're picking out a single point in each elliptic fiber. This is giving you a natural value of the axiodilaton at each point in the base. And so having that single section, quite useful. Okay, just in a little bit more detail, if we have an elliptically fibered manifold X over B, writing this in the P1236 description of the elliptic fiber, we can write a Weierstrass model as given by these degrees, where here these coefficients would live in K of the base to the -4 and -6, respectively. Again, degenerations of the elliptic fiber would encode information about 7 branes, and for this simple form of the elliptic fiber, the discriminant is easy to write down algebraically. This is the locus where the elliptic fiber would degenerate. Divisors inside the base that support such degenerate fibers, these would correspond to gut symmetries in F theory. In general, if you were to resolve those singular fibers, then these would form the affine Dynkin diagrams of the gauge groups of interest supported over the 7 branes. So for example, the affine Denkin diagram of E7 would be built over some divisor in the base, where one of these nodes in the affine Denkin diagram would be intersected with the zero section, which would not be blown down in the Weierstrass limit, and hence this would form a gauge group of E7. Intersections between divisors would correspond to matter. Okay, so with that one page intro to F-theory, for those of you that aren't familiar with it, what is the takeaway? Elliptic fibrations encode information about strongly coupled type 2p. Moreover, there is another way to think about F-theory, which is perhaps more useful, which is as a limit of M-theory. So M-theory, F-theory duality roughly states that if you have M-theory compactified on a Calabi-Yau n-fold, this should be dual to F-theory on the same Calabi-Yau n-fold times S1 in the limit that the elliptic fiber goes to zero volume. So M-theory on the resolved manifold would be the Coulomb branch of that theory. I'm going to be focusing in this talk on 6D5D, and the states of the physical theory are actually determined by the geometric data of that resolved manifold in a very simple way. For example, the multiplicity of fields, the numbers of tensor, vector, and hypermultiplets are counted by the Hodge numbers of the manifold in various combinations. Anomaly cancellation conditions in 6 dimensions place very strong constraints on these degrees of freedom. Moreover, there's a powerful theorem due to Shioda, Tate, and Wazir, which says that specifically if you're interested in divisors within the elliptic threefold, every divisor can be put into one of 3 boxes. Either it is the pullback of a divisor from the base, in which case it's counting as a tensor multiplet. It is a zero section or an element of the Mordell-Weil group of the manifold, i.e. the group of rational sections of that fibration. And these are counting as U1 factors in the gauge group, or it is a reducible component in the divisor, a so-called fibral divisor, which will count for non-abelian gauge degrees of freedom. So again, simple ingredients in geometry allow you to read off important properties of the field theory. Now, I need to, again, focus on some of the differences between elliptic and genus 1 fibered manifolds. So as I've mentioned, F-theory was sort of naturally defined on Calabi-Yau fibrations with section. Elliptic n-folds in Weierstrass form can be systematically constructed very straightforwardly. Again, Morris and Taylor over toric surfaces is an example of a large data set of this type. But if I'm interested in the question of what Calabi-Yau threefolds can I build, and hence what field theories can I write down, one question you might ask is, okay, if I don't have a section, if I only have multi-sections, what to do with the genus 1 fibered manifolds? So there have been no systematic data sets of elliptically, or excuse me, in this case, genus 1 fibered manifolds. This is built the same way that elliptically fibered manifolds have been built. And part of the goal of the work that I'm going to discuss today is how to sort of ask the question, if I'm building a large data set, how different can the genus 1 fibrations look from their elliptic cousins in a way that I'll make clear in the following slides. So for starters, I know that genus 1 fibered geometries are perfectly fine backgrounds to M-theory in various dimensions, i.e. if I compactify M-theory on a Calabi-Yau threefold, I would have a 5-dimensional effective field theory coupled to gravity. And via M-theory, F-theory duality, the existence of that T2 fiber would certainly lead one to expect an uplift of M-theory on genus 1 fibered manifolds to F-theory vacua. And indeed, from the early days of F-theory due to Morris and Vafa, and then elucidated a number of years ago by Morrison and Taylor, you can make that type of correspondence very explicit for genus 1 geometries of a simple type. So M-theory on genus 1 fibered manifolds uplift to F-theory on the so-called Jacobian fibration of that threefold. So the idea is that the Jacobian of an elliptic curve, this is the set of degree 0 line bundles on that elliptic curve, is in fact diffeomorphic to the elliptic curve itself. So for a fiber, we could replace each fiber of the genus 1 fibration with an additional, with a new fibration, let's call it J of X over B, which is replacing each fiber by its Jacobian. In general, the Jacobian is defined only up to birational equivalence, but clear that such a thing should exist from the construction of Jacobians of single elliptic curves. So for genus 1 fibered manifolds, constructing the Jacobian will lead to an elliptic fibration whose fibers share the same tau function. Remember from our definition of F-theory as something that's tracking the axiodilaton of type 2b, this is exactly what you want and was pointed out by Morrison and Vafa in early days. There are also many techniques known to construct these things algebraically. So you hand me a genus 1 manifold, I can build the Jacobian fibration very explicitly through algebraic constructions. For Calabi-Yau elliptic fibrations, I should point out that you could also write down the Jacobian fibration, and that would indeed be birational to the Weierstrass model. For K3 surfaces, these are in fact identical. So a K3 Weierstrass model and a K3 Jacobian fibration does nothing to it if you take the Jacobian. For Calabi-Yau threefolds, you can have differences in the fiber at higher codimension. For genus 1 fibrations, there is no version of Nakayama's theorem, so we do not have Weierstrass models available, and so Jacobian fibrations are the only possibility. One property of this construction, which I don't have time to go into in detail, is that the location of singular fibers over points in the base, i.e. the discriminant loci of these two fibrations, must agree. And this provides some powerful insight into the structure of both the Jacobian and the original genus 1 fibered manifold. Importantly, given a single genus 1 fibered manifold, there is a unique Jacobian elliptic fibration. However, there can be many different genus 1 fibered manifolds which share the same Jacobian. And in this sort of set of different geometries which share a Jacobian are referred to as the the Tate-Shafarevich group. In general, in the case of multiple fibers, this should be expanded and referred to a bit more broadly as a set of Calabi-Yau torsors. Okay, so I've argued that elliptic Calabi-Yau threefolds generally easier to algorithmically construct and analyze than genus 1. The idea in the F-theory literature to date, and one could again approach this systematically within building Calabi-Yau threefolds, is to use the Jacobian to characterize genus 1 fibered manifold. Important questions that you want to ask in this context, and again, this is where the broad scale, what is possible within Calabi-Yau threefolds becomes important. You want to ask how similar or different can a genus 1 fibered manifold and its Jacobian be? For example, must they share certain Hodge numbers, certain gauge groups, i.e. the fibril divisors that must appear in this fibration? What can you read off that should be the same or different? And this has really been studied in great detail for the case of abelian gauge groups, but I want to illustrate some open questions in the case of non-abelian gauge groups. Okay, so here is a simple example of a genus 1 fibered manifold, which actually led me to the work that I'm talking about in this talk. So this was an example that was noticed by Paul Ullman, which was a Calabi-Yau threefold, which is genus 1 fibered over a simple base, dp1, and it exhibits, it has a bisection and exhibits a gauge group of F4 times U1 in the 5D theory. It can be described as a simple resolved quartic hypersurface. Nothing particularly special about this geometry. The interesting feature of it, though, is that this theory that would have an F4 symmetry in 5 dimensions, i.e. F4 reducible fibers realized in the discriminant locus of that fibration, is that its Jacobian exhibits a different gauge group. Its Jacobian is in fact an elliptic threefold with E7 non-abelian gauge group. This also has discrete gauge group factors and terminal singularities, as I'll talk more about in a second. So here is the Jacobian. So the Jacobian can be realized as a tuned version of a Morrison-Park type model of a geometry with exactly 2 rational sections written as a hypersurface in a blow-up of a simple projective space, simple algebraic form. And by tuning coefficients to certain orders of vanishing, we can see that we can construct both quartics and their Jacobians constructed here, such that the genus 1 fiber and the Jacobian fiber would agree in their non-abelian gauge group. This E6-2 is, as I'll talk more about in a second, an affine folded version of F4. This leads to an E7 fiber, and we can also have other tunings which could give smaller gauge groups. Okay, so what, you might say? So the interesting thing about this is how the gauge groups differ between the Jacobian and the genus 1 geometry. So the structure that I'm illustrating here is going to be for the E7/F4 case, but the structure, as I'll talk more about, is extremely generic in all examples of this type that we found looking at toric data sets. So what you find is that you end up with something that looks like the affine Dynkin diagram of E7 realized inside the genus 1 geometry. However, the intersection structure with the multi-section, illustrated here by these little dotted circles, actually makes homologically equivalent certain fibril divisors. So again, the Dynkin diagram that I'm drawing here should be viewed as reducible components in the resolution of singular fibers. And the monodromy, as I move around the base, links together certain P1s in the fiber into classes, which tell you that this is no longer an E7, but actually in this case, an E6-2, i.e. an F4. So the 2-section monodromy exchanges fibril divisors. These have been given particular labels for which P1s are being intersected here. And in general, this is folding the affine-Dinkin diagram of the elliptic Jacobian. So let's look now in field theory at sort of what we expect to be happening in F theory, M theory, and then again, what can we say about this type of difference generally? So if you say nothing else about how these are related, except that I should be able to define F theory vacua on things with elliptic fibrations, and on genus 1 geometries, I should be able to define M theory vacua. It's easy to read off that you have a chain of possible theories in 6 and 5 dimensions. So 6D, 5D written here, where the starting theory in this case is actually in the Jacobian and E7 times U1 mod Z2. There's a non-trivial global structure in this. Upon dimensional reduction on M theory on the same manifold, you would have in principle an E7 times U1 times a U1 KK. But by looking at these other possibilities in the genus 1 geometry, it should also be possible to have, for example, E6-2, which should be related. So this should be the M theory, and the 6DF theory should be related to a particular Higgsing of the Morrison-Park model I mentioned earlier. Okay, so all I'm saying is you have this set of manifolds. They differ in a certain way in their gauge group due to monodromy of the multisection. And now you know that certain vacua of M theory, F theory exist. So the game is, can you explain what the rules are for these dimensional reductions and also geometric transitions between them? Let me review then what we understand, which is quite a lot, about how M theory and F theory are related on genus 1 manifolds. So the idea, again, this was first written down by Morrison and Taylor. M theory on genus 1 compactifications in 5D should correspond to F theory compactifications in 6 dimensions on elliptic threefolds with discrete symmetries. In order to match the 6D and 5D theories, I need to take the 6D F theory compactification, add an additional S1, and attempt to match those two field theories. So in this case, if we begin with 6-dimensional F theory on a Calabi-Yau threefold with 2 rational sections, i.e. a rank 1 Mordell-Weil group, there will be a U1 factor in the gauge group, and we can require that there be a field of charge Q under that U1 in the effective theory in 6 dimensions. Now, of course, giving a VEV to such a charge field would break U1 to a discrete subgroup. And in principle, it is possible to compactify on S1, where this field will have a non-trivial profile over the circle direction, here labeled Y, in the following way. You can also turn on flux, i.e. a Wilson line along that S1. This is a non-trivial background value for gauge fields along the circle. Under dimensional reduction, there'll be kinetic mixing between U1 KK and U1 6D, and this gets mapped very explicitly into the multi-section divisor of the 5D Calabi-Yau threefold. So the basic structure is, in the case of zero flux, M theory on elliptic Calabi-Yau threefold with torsional cohomology and terminal singularities can lead to a U1 times ZQ theory in 5 dimensions. And if the flux is non-zero, then we obtain M theory on a genus 1 Calabi-Yau threefold with multi-section of order Q and a single U1 factor. So in general, the possible choices of VEVs for charged matter and fluxes along the circle correspond to distinct M theory vacua in 5D, and hence different elliptic genus 1 fibered manifolds, which importantly all uplift to the same F theory physics in 6 dimensions. Geometrically, this says there's a set of Calabi-Yau threefolds which have the same Jacobian, namely the Tate-Schafferevich group is the set of the manifolds that we're interested in. So all of this well understood and well studied in recent years for the case of abelian gauge group factors. So now the interesting additional ingredient that I want to add is more general possibilities in the case that we have non-abelian gauge group factors. So in general, a 6D group like G times U1 to the R. So here we could imagine more general choices of Wilson line. You could have fluxes associated to both the non-abelian and abelian gauge group factors. I'm going to refer to those as psi sub U1s from the abelian factors and psi sub G. The latter, of course, as a set of fluxes is well understood for circle reductions, would embed into the Cartan of G. And in general, if you turn on however many of these, you would break to U1 of the rank of G. Okay, nothing particularly mysterious so far. But there is an interesting possibility in the presence of these non-abelian factors. In addition to these non-zero gauge fluxes along the circle, there's also the possibility to induce a so-called twist. So these are very familiar in field theory in various dimensions, but have been less studied in the context of F-theory in particular. So much recent work is studied in the context of gauge theories, twisted circle reductions, and more recently in the context of SCFTs in 5 and 6 dimensions. A very non-complete list of recent work on this involves work by Tachikawa, Bardwaj, Jefferson, Kim, Tarzani, and Vafa, and Kim, Lee, Yi, and Yi. So I want to take a look at the physics of these reductions for a moment and then map this into the explicit Calabi-Yau geometry I introduced a few slides ago. So what is the observation? Circle reductions of gauge theories with discrete global symmetries could lead to the possibility to introduce non-trivial boundary conditions on fields around the circle, i.e. non-trivial holonomies, that can non-trivially twist the resulting theory in one dimension lower. So the natural sort of discrete choices that you would have for a non-abelian gauge group correspond to the set of outer automorphisms of that group. So the basic idea is that as you move around the circle, in addition to just turning on a non-trivial profile for gauge fields around the circle, you can also use outer automorphisms to, as you move around the circle, identify different elements of the carton to map pieces of the gauge group into one another. This sort of naturally has to be a group of outer automorphisms. If you use inner automorphisms in the gauge group, that can be undone by gauge transformations in an easy way. So the outer automorphisms are not elements of the group, but they are discrete transformations which respect the symmetry of the theory. So the basic idea here is I'm going to start with an AMU, which is defined over my full F-theory background plus the circle, where y is the variable describing the circle direction. And as you move around to pi, you can come back to yourself up to an action of sigma on the gauge fields, where sigma, in this case, is an outer automorphism, element of the outer automorphisms. It's well known that these outer automorphisms can be identified with graph automorphisms of Dynkin diagrams. And this has been used in many contexts in string dimensional reductions in field theory to date. So as a simple example, outer automorphisms of E6 are Z2. So you could begin with a d-dimensional E6 gauge theory, and upon compactifying on a circle, you can produce an F4 theory in d-1 dimensions. This corresponds to, quote, folding the Dynkin diagram. So E6, various automorphisms, you can identify the nodes of your Dynkin diagram with each other and, quote, fold the E6 Dynkin diagram to F4. So this has led, the structure that I've described has led to many interesting novel effective field theories in assorted dimensions. One example in the heterotic string is the so-called CHL string. This is an example of such a theory. So if we begin with the 10-dimensional E8 cross E8 heterotic string, there's an outer automorphism between the two E8 factors, a Z2, which exchanges those E8 factors. And we can dimensionally reduce on S1 and twist by that Z2 to produce a 9D theory, for example, with gauge symmetry E8. So breaking to the diagonal E8 across those two factors, or various subgroups, depending on choice of bundle. Other examples of using this twisted dimensional reduction automorphisms of Dynkin diagrams, as I mentioned, you can twist E6 by a Z2 to produce S4, F4, SO8 by a Z3 to produce G2, SU2M to SO, odd SUs to even SUs, and so on. So well understood how to do this in gauge theory. So why am I describing this as something novel and or mysterious in the present case? A slight hitch in this picture arises when we couple in gravity to these gauge theories. So twisting by an outer automorphism or any other discrete group is perfectly fine for gauge theories in various dimensions, but new questions arise in the context of gravitational theories, specifically about what types of global symmetries are allowed. So much recent interest has centered on swap-line conjectures, and one of these, which is very well known, is that gravitational theories with global symmetries are not UV completable. So the punchline of this is that we expect that the discrete global symmetries one would hope to twist by must actually be gauged in the complete gravitational theory. In some contexts, this is quite clear how this happens. So for example, for the CHL string, the Z2 symmetry that I described of switching E8 factors is upgraded to a diffeomorphism of the S1 mod Z2 interval in heterotic M theory. So it's clear that these things can be completed in string theory. The question simply is how. So now, with this field theory review in hand, let me now return to the question of how different can a genus 1 fibered manifold and its Jacobian be, and how does this work with dimensional reductions of M theory, F theory? So inspection of toric Calabi-Yau threefolds yields many examples of CY threefolds for which the non-abelian group realized between the genus 1 and its Jacobian is different. The first examples that I'm aware of this appeared in a paper by Brown and Morrison, and it is simple to enumerate, again, based on known data sets, what is possible. The foldings that appear to be foldings, as in the E7 example that I mentioned, of affine Dinkin diagrams. So affine E7 with a Z2 folding leads to E6-2, namely an F4. Affine G2 appears, that leading to SU2 upon folding, affine F4 with Z3 folding. So it seems that something very similar to these twisted dimensional reductions is happening in the M theory, F theory relationship between these geometries. The basic observation, though, that we see is that it's not folding of Dinkin diagrams that appears to be happening in the genus 1 geometry. It is actually affine Dinkin diagrams that appear to be folded. Now, at some level, that's unsurprising because, as I mentioned previously, it's actually the affine Dinkin diagrams that are realized in the reducible fiber structures of the resolved Calabi-Yau manifolds in their resolved M theory limit. But nonetheless, the gauge groups that are appearing are not the affine groups. They're, of course, only the finite groups. So just as a enumeration of possibilities, you can write down known foldings of affine Dinkin diagrams. Here, the black dots denote the affine nodes. Deletion of this node would result in a finite algebra. Here's the example I've talked about already, affine E7, which folding, identifying these nodes, and then deleting the black one can lead to F4. Likewise, lots of other possibilities, E6-1 leading to D6, D4-3 leading to G2, and so on. So basically, if you look at the known foldings of affine Dinkin diagrams, all the ones that are known appear to be realizable within toric constructions of Calabi-Yau threefolds with genus 1 vibrations. So let's put these pieces together now. The observations that I made so far is that you can see affine foldings in genus 1 geometries. Again, the reason that you care about this question from a sort of broad Calabi-Yau geometry point of view is you want to say, I would like to characterize both elliptic vibrations and genus 1 vibrations as tightly as possible. And I want to know how much I can use the Jacobian to classify the genus 1 geometries. In principle, this should be fully possible, but you need to, again, understand how different these can be. So one question you can ask is this sort of affine folding that we're saying the only possibility? And then field theoretically, what is the F theory, M theory correspondence for these geometries? So it seems natural, again, as I mentioned previously, that these genus 1 geometries should arise as twisted circle reductions of F theory on their Jacobians, but you have to understand how to handle the affine nature of the folding that you're seeing. The gauge symmetries are the gauge symmetries are only the finite pieces of these affine groups. So how to understand the boundary conditions, same point. And then how are these discrete folding automorphisms realized, again, in this no global symmetries constraint, how are they actually realized as local gauge symmetries in the F theory geometry? So it is a nice bit of structure that, in fact, the origin of the twisting symmetries. So where are you going to pull discrete symmetries from the threefolds that do what you want in terms of identifying nodes of these Dinkin diagrams? There is a natural candidate. As mentioned above, we expect discrete twisting symmetry to be realized as a diffeomorphism of the Calabi-Yau threefold in M theory. And looking at what must happen in terms of beginning with, for example, a G times U1 theory, and then being able to reduce that to the twisted affine folded group times U1 in 5 dimensions, it's clear that your symmetry had better be able to mix elements of the carton of the non-abelian group in U1, as well as permuting elements of the carton within the non-abelian factor. There's a natural candidate for an action on the Calabi-Yau threefold that can do something similar to this, which is the freedom to choose a zero section in an elliptically fibered geometry with multiple rational sections. And this was laid out very clearly in the structure of 5D to 6D dimensional reductions by Grimm, Kapfer, and Cleavers. And the basic idea is that from the point of view of M theory geometry, we're sort of breaking up the reading off the field theory in terms of pieces that will be uplifted to 6D F theory in terms of where the divisors originate within Chiyoda Tate Wazir. So their decomposition of divisors. So does it come from the base? Is it a section, a rank element of Mordell Bay, and so on? That characterization of fibril divisors and how everything behaves is made with respect to one zero section. But of course, you're free to choose any rational section to be the zero section of your Mordell Bay lattice. And so what Grimm, Kaffer, and Cleaver showed is that if you choose different zero sections, in the case that you have many available to you, these multiple rational sections lead to an interpretation in the 60-dimensional reduction of that field theory as integral large gauge transformations around the circle. So just to say that again, multiple rational sections correspond to an addition law on each elliptic fiber. The zero is an arbitrary choice from the point of view of the M theory geometry. And so in order for F theory to make sense for all these possible uplifts, this has to be understandable as an action on a circle reduction. That circle reduction can be viewed, can include large gauge transformations that are integer valued around that circle. These guys, Grimm, Kaffer, and Cleavers wrote this down for abelian gauge theories. This also studied some non-abelian gauge transformations within this process. And they very clearly wrote down 5D to 6D uplifts. So for the present case, what kind of ingredients do we have? The resolutions of the Jacobian manifolds, i.e. 3-folds with E7 times U1 mod Z2 global symmetry, these exhibit a non-trivial Z2 symmetry upon interchanging the two sections in the Mordell-Weil group. You have to consider the action on the Schrödinger maps. This flips in the affine Dynkin diagram that is being folded in the genus 1 geometry. This actually flips the affine and fundamental nodes in the affine E7 Dynkin diagram. And it will shuffle Dynkin multiplicities in the way that you would expect. It corresponds to U1 charge conjugation, which is again, as expected for the action of something similar to an outer automorphism, and has a fixed point of F4. So this is to say that section interchange can lead to symmetries of the M theory effective physics, which might be interpretable in circle reductions of M theory. The details of this are surprisingly subtle, and part of what we're attempting to finish in the paper that we have soon to appear is some subtleties to do with this point. But the basic structure holds. I'm almost out of time, so let me just say briefly a few words about, again, structure that you would like to understand. So a powerful tool in understanding 5D to 6D M theory, F theory reductions is to be able to consider elements of the Tate-Shafirevich group, compactify F theory on each one, and then ask how are those geometries related to each other in 5 dimensions. So this was first done by Grimm and collaborators in great detail, where you can, for example, do the sort of naive trivial reduction of the Jacobian, which would correspond to the Jacobian in F theory and then M theory compactified on that same elliptic manifold. That's sort of the most basic, everything in the 6D theory is being copied as tightly as possible in 5D. And then for these different choices of fluxes or boundary conditions, you can ask, what are those other Calabi-Yaos that I would have in M theory and 5D? And then how do I transition between the two? So in the present examples, we can control those conifold transitions very explicitly. And I'm showing just a schematic nature of these sort of twisted versus untwisted dimensional reductions. We have a set of parent theories that I've labeled A, B, and B/C and D here, which would correspond in the 6D physics to Higgsing transitions, which correspond to webs of singlets or to charged matter. And you can have untwisted dimensional reductions, which lead to theories in 5 dimensions with sort of well understood structure that are coming very directly from the 6D physics. And you can have twisted reductions where here things like G twiddle are the folded affine realization of G. So E7 going to F4, for example. These conifold transitions are extremely important in terms of, again, understanding sort of at a fundamental geometric level, how do you split the sheets of multi-sections or bring them together? And how do you actually realize this affine folding? And what are the possibilities within the Calabi-Yau 3-fold geometry? Just one comment that I'll make in the context of the particular example I told you about today in this E7 geometry is that things like these non-trivial boundary conditions, which are identifying nodes of Dynkin diagrams moving from 6D to 5D, can actually be realized, the folding is realized very explicitly as ordinary Higgsing transitions in 5 dimensions. So it is possible to write down a 3-fold for which the full E7 symmetry is realized in 5 dimensions, give a bev to a 56 of E7 and break to F4 in sort of a well-understood way. But moving from 6D to 5D then is a much more subtle process. So these Higgsing transitions are important both from controlling the field theory and its uplift, and also to be able to say what is possible more generally for genus 1 and their Jacobian. So with that, I think I am basically out of time. Let me just summarize. Points that I've tried to get across broadly in this talk. are that I hope I have at least sketched some of the reasons why Calabi-Yau fibrations form a rich arena for studying Calabi-Yau geometry in general and string dualities and spaces of string vacua associated to them. The characterizing genus 1 geometries as opposed to elliptic geometries and the relationship to their Jacobians has consequences for the string landscape. And compared to the elliptic case, there has been much less work systematically building large data sets of Calabi-Yau threefolds and understanding the geometric transitions that can link them. Not all twisted dimensional reductions of gauge theories appear to be realizable within M theory, F theory reductions. So for example, a pure E6 theory, which at the level of a gauge theory could be folded to F4, does not appear to arise within the known data sets that we have. Instead, the affine foldings appear to be what the genus 1 geometries actually realize. This tells you that the U1 factors in the gauge group play a crucial role, and I've sketched that as a diffeomorphism of the Calabi-Yau threefold, the choice of zero section, which you only have in the case that you have multiple U1 factors, multiple sections and hence a U1 factor, are playing a key role. And it would be interesting to understand if the foldings of the type I've described are in fact the only possibility for, again, moving from a Jacobian to a genus 1 and how they can be related. The broad question that this touches on at the level of geometry is how disparate can elements of the Tate-Shafarievich group be, i.e. if you have a set of threefolds that share the same Jacobian, how many different features can they have, and can you enumerate that in a systematic way? There are many open questions to that, but I hope we're taking some steps in that direction. And I'll stop there.
Thank you very much for the lovely talk. Let's take some questions. If you have a question, please unmute yourself and ask. Gonçalo?
Oh, hello.
Hi.
So I was wondering, how is it that you detect whether one of these Calabi-Yaus that comes in these big lists is fibered or not, and in which way?
Right.
Do you have like a programmable way of doing that? Or?
Yes, indeed. Sorry, there's a whole separate talk that could be given on that, and I did not tell you about that at all. But yes, indeed. There is a criteria that is sort of easy to write down in terms of the triple intersection structure of a Calabi-Yau threefold for the existence of a fibration. This was conjectured by Janos Kollard that this should actually be if and only if for Calabi-Yau threefolds that admit fibrations. So this Kollard type criteria is sort of, it's something that's easy to algorithmically implement if you understand the Kähler cones and the intersection structure of a given threefold. The hard part to do sort of for any mystery manifold is the Kähler cone. The effective, that you need the cone of effective curves and the Kähler cone to write it down. So in the work that I've done, that's been the real limiting factor, is being able to find sets of threefolds where you have complete control over the cones. If you have the cone structure, then it's pretty easy to enumerate whether there will or will not be a fibration.
Okay.
Happy to provide some refs for that offline if you shoot me a message or something. But yeah, I did not talk about the details of that at all.
Thank you.
Ling?
Yeah. Hi, Lara. Thanks for the nice talk. I had a question regarding this twisted compactifications. So I remember the physics context was mostly in terms of the engineering of 5D SCFTs and their relation to now 6D SCFTs on a circle. So in those cases, the manifold is typically non-compact, right?
Mm-hmm.
So
That's right.
how,
and so,
do you have a, yeah.
Great question. So in that, this is work of Vafa Jefferson et al., right?
Right.
In their context, they certainly consider cases where sort of the foldings of ordinary Dinkin diagrams are appearing. And that's an interesting question. I mean, what we seem to be seeing is that when you move to the compact geometry, you can't do a lot of the stuff that that they would write down in the non-compact case. I should be careful in that this is, sort of known data sets of threefolds that I know how to analyze. And of course, they're looking at the non-compact setting and they're sort of building everything up in this nice modular way of intersecting surfaces. So I think there are some open questions about what the possibilities are there, and I would like to understand that better. Certainly in terms of the no global symmetries conjecture, I think it's clear that you cannot use ordinary gauge theoretic autoautomorphisms the way that you would in field theory, right? You have to interpret them in a more sophisticated way in terms of the Calabi-Yau geometry. So we figured out how to do that in certain classes of geometries, but again, there's open questions about what are the full range of possibilities.
Okay, cool. Thank you.
Gonçalo again.
Sorry for asking another question. So I was wondering, I'm very not an expert on this. I was wondering about these interesting figures that you obtain when you plot the odd numbers of these Calabi-Yaus. And I was wondering, one can consider, for example, for each transition, a dynamical system on these transitions given by what it does on the odd numbers. So for the conical transitions, it kills something in H30 for Calabi-Yau threefolds and creates something in H11. So you can create this dynamical system, this operator that does something. And I was wondering if this figure
these curves,
is approximately closed under this operation.
It's a great question. There's a lot of substructure in these plots of Hodge numbers. I know that Philip Candelas and collaborators have a paper from like 5 years ago where they were sort of trying to phrase in as you're saying, in sort of broad a context as possible with geometric transitions, sort of what are the rules for what those curves can look like, excuse me. You can also ask that question in field theory. So you can say within a class of compactifications, there are known transitions in field theory I can do. For example, Higgsing transitions in F theory on threefolds. And then, can I plot my path along these Hodge numbers through those? And that matches for like F theory in 6 dimensions extremely well. So Waddy Taylor has done work on that where you can just sort of line up where all the points have to be based on consistent field theories in 6 dimensions. I think your question is a little bit more broadly, just geometrically, can I see independent of field theory what the rules might be? And again, I think the answer very well may be yes. Yeah, you could ask that question in either context, I think. Okay, so I'd say, yeah, Candelas and Taylor would be the ones to look at on that.
Okay, Candelas and Taylor. Thank you.
If there are no more questions, let's thank Lara again for the great talk.
Thank all the speakers of the day.
And we will reconvene tomorrow morning.